I'm sorry, I messed up printing the handouts today. So I think you only have like page 1 and 3, I guess. Yeah, because I made a mistake. So yeah, the physical handout is useless. So I will try to make sure that this one is always pointing to the right thing. Chalk. Okay, so I know it's been a little while since we did set theory because of break last week. So just to remind you all where we are, we have talked about finite and countable sets now, and the plan is to start talking about sets which are larger in size. Okay, so we want to develop the theory of like infinite sets with a focus on the uncountable ones, which are bigger than countable ones. Okay, so we know a few sets which are bigger than countable. Examples of uncountable sets. So some will be like the reals is uncountable. The complex numbers are uncountable. The irrational reals, those are all uncountable. And in fact, these all have the same size and the same cardinality. You can prove that's not too hard to do so. So if you want something bigger, then you could take the power set of one of these. That's necessarily bigger. Power set of reals. We know this by Cantor's theorem. What is going on outside? And if you want something bigger than this, we could take a power set again, and so on and so on. But you'll find if you, in your mathematical lives, that if you actually like come across a set that is uncountable, it's usually this size or this size. And you know, other stuff just doesn't come up very often. Like maybe you'd get like a second power set here, but there'll usually be like a small number of power sets of the reals. So the question that kind of guides us is, well, we know theoretically that there are more than this, right? Because we can keep taking power sets and they keep getting bigger and bigger and bigger. So you might have a question like, is there anything that falls in between them? Like, is there a size that's strictly between these two? And more simply, is there a size in between that of the reals and the naturals? So the claim that there's nothing in between these two, there's just size of the naturals is the smallest infinity, then size of the reals is the next infinity. That claim is called the continuum hypothesis. The continuum hypothesis says if there's lots of different ways to say it. The size of omega is less than or equal kappa is less than or equal to the size of the reals, then kappa is the size of omega, or kappa is the size of the reals. Okay, so this problem was one of Hilbert's problems, which he set out, I think it might have been like the first or the second, just to start, like solve this problem. Is the continuum hypothesis true? At the beginning of the 19th century. No, 20th century, beginning of the 1900s, 20th century. And it turns out whether this is true or false is independent of our axioms. And it's still an open question among set theorists whether we should add more axioms to our list which would decide this problem. And there's not agreement, actually. There are working set theorists who believe the continuum hypothesis is true. There are working set theorists who believe that it's false. And there are some who believe that that question doesn't really have a definitive answer. So the state of the art mathematically is that based on the axioms of ZFC, which we very nearly listed all of them now, all we're missing is replacement and foundation. Based on all those axioms, we can't tell if this is true or false. Yeah?
How would you know that we can't tell? There's no way there are axioms to tell that.
That's a very interesting question, which has a lot of very difficult mathematics behind it. But on a very basic level, to show that there's this thing called the completeness theorem that says if I can prove something based on some axioms, then in every structure satisfying the axiom, that statement is true. So it says truth and provability are the same. So what that means is you can show something can't be proved by providing a counterexample, right? Which is a very natural mathematical thing. So what you need to do is provide a structure that satisfies the axioms of ZFC, but does not satisfy this, and one that does. So you need to build a universe of sets. And that's actually quite difficult because of the incompleteness theorem that says ZFC can't build something that satisfies all of ZFC at once, roughly speaking. Oh, I should say the one tiny caveat is that provided ZFC is consistent, right? So we know naive set theory is inconsistent. We've proved the inconsistency, right? Russell's paradox. We believe ZFC is inconsistent because we haven't found a paradox yet. But ZFC could never prove it is itself consistent unless it is inconsistent. Inconsistent. So the only Gödel's completeness, second incompleteness theorem says any axioms that prove that they are consistent are themselves inconsistent. So we're in this permanent state of forced agnosticism based on just features of the logic, which is very frustrating if you actually want to answer questions. But yeah, building structures which do and don't satisfy various axioms is quite difficult. And there's a few different methods, and unfortunately there's no class here that will teach you how to do it. You have to go to a different school if you want to learn how to do that here. I'm sorry. It's not my fault. I don't hire the professors who work here. Okay, so what I'd like now is some more terminology to talk about questions like this, right? We have infinite sizes of different kinds. I'd like a more systematic way of talking about them. So we have informally been talking about cardinals a bunch, right? And so far, formally, this is an abbreviation for a claim about bijections existing, right? Or injections existing, right? So saying if I write this, the size of the reals is Aleph0, right? This is literally an abbreviation that means there is a bijection between this and omega, right? And if I say the size of something is 6, that's an abbreviation that means there is a bijection in it and the set we call 6. Okay, but it's very helpful to think of this as an object, right? This is a number, and I mean there's a bijection to this number, okay? And so what we want to do is pick out a set for every particular size. And so that is the size, that is the number we're going to call that. And we've done it for the finite sets, right? The size 0 is represented by the empty set. The set 1 is represented by, the size 1 is represented by the set containing 0. The size 2 is represented by the set containing 0 and 1. Right, and we've actually and I want to do that for all the infinite sets. So I want a particular set that works for every size, and I want just one that works for every size, and I would like a definition of that which isn't like circular, right? So I'd like to say you are a cardinal if, and then some set theoretical properties which are not circular. So I want a precise definition. Okay, so working up to that is actually quite a pain. So we're going to have to do that now over the next couple days. Also, these last 2 weeks, we're going to start moving pretty fast. I'm going to make some claims and just, like, we're not going to prove them in detail. And hopefully you'll just believe me. Because I have a goal that I'd like us to get to at the end of the class, which is completely have all of our axioms, have all of our, have our cardinals, have ordinals, and then be able to talk about the von Neumann of the universe. And then we'll be done. All right, so to do this, the idea is we've got finite natural numbers, right? We've got aleph 0, which I've said will be the size of omega. And those sets have various features, right? Finite sets and omega, they actually have two features. I mean, they have lots of features in common, but the two features that turned out to be interesting for us are they are both well orders. All of them are well orders, and they're all transitive. And it turns out that's a really excellent starting point. But before I talk about that in detail, I better clarify what I mean by a well order. Okay, so cool. Less than on A is a linear order, and I guess I should write strict here. It's a strict linear order, right? And by strict I mean you're not less than yourself, right? That's less than or equal to. If, and I put recall here, but I can't remember if I actually defined this before, so this might be definition. But if I have, then we're fine. Let me get the right note so I don't get it wrong. If less than is transitive, in the normal sense, right? A less than B and B less than C means A less than C. Asymmetric, which is different than antisymmetric, which we've already defined, and total. Okay, so asymmetric means it's never symmetric. Not that it's not. So symmetry of a relation means if A is related to B, then B is related to A, right? So not being symmetric means there is some pair where A is related to B, but B is not. Asymmetric is there is never a pair. So strengthening. So this means if A is less than B, then B is not less than A. Never symmetric. Not that, even in one place. Total, we've defined before, it means if I have two things, either one of them is less than the other, as long as they're distinct. If the distinctness is important here. So if A is not equal to B, then A is less than B, or B is less than A. And in light of asymmetry, it's exactly one of those, right? Can't be both. Yes, Kai. It's only a tiny bit different because of trichotomy, I assume, reflexivity. So that you could state this as a trichotomy law, which is also fine. But I wanted to state it differently to not confuse it with that one. So less than equal, that's all. But it is, these two are exactly trichotomy. Yes. Exercise. Prove that. I mean, obviously, you've already done that in your head. But no, those are correct. Okay, so this is a strict linear order because we're not allowing things to be less than themselves. I know we've dealt with non-strict before, but it's more convenient for well orders to talk about strict less than. You'll see why. And okay, so further, less than is a well order. It's an unfortunate linguistic thing here. This is using the word well as an adjective, but well is not an adjective in English, right? So some authors write this, and sometimes I write this, sometimes I don't. Everything's fine. We'll all understand. But it's a well order if it is linear and the well order part. So the well order part for the natural numbers, that's the same as the well order part for this. So it's whenever we have a non-empty subset of our field, there is a less than minimum element of B. That B is not very good. Looks more like a beta. It's a beta B. Anyway, so what by this I mean, there is an element of B which is less than every other element of B. That's what it means to be the minimum, right? You're less than everything else. Okay, so examples of well orders that we've seen so far are omega itself is well ordered, and each natural number is itself well ordered by the restriction of the less than relation to it. So examples. Omega and every n in omega under the element relation, right? So remember, for us, by convenient feature of our definition of the natural numbers, right, less than is the same as element. Okay, so these are both well ordered under element. Non-examples, right? The integers is not well ordered under its standard less than, because it itself has no minimum element, right? There's no smallest integer. Same for the reals, same for the rationals. Okay, so what's good about well orders is there's really only one way that they look. And we can draw really easy pictures of them by starting with the least, and then picking the next least, and then picking the next least. And I can always do this just because of the definition of being well ordered. So if we were to draw one, here. So I've drawn these pictures before of orders, right, where the things at the bottom are smaller than the things below, and there's lines between them to show comparability. Right, we've done that with like power sets and the subset relation and so on. So well orders have so much structure that there's only really one way this picture can look. So because well orders are well ordered, right, if I have the whole thing itself is a non-empty subset of itself, like assuming A is non-empty to start with, which means it has a least element, right? So a well order has a least element. Non-empty well order, I should be precise. So we can start with this guy down here. It's the least element. So let me call this W0. Okay, so this is our least because the set W that we're well ordering has a least element. Okay, so there's nothing below it. Is there something above it? Well, probably. Well, it depends on what W is, right? Like, if W only has one element, then we're done. But otherwise, there's stuff that's left. So what do we know about the set W, except we take out the smallest element? So let's look at our axioms. It does, yes, indeed. So if this is non-empty, then everything in it is necessarily bigger than this, right? Because of totality. Right, they're all comparable, so, and because this is minimum, that means this is the smallest. What else do we know? It itself has a least, right? So that means I could draw a little thing here, and then write a W1, right? So there's a next guy. It's not like the rationals where there's no next biggest thing, right? In the rationals, there are things that are bigger than you, but there's no next biggest. Okay, so now we've got W0, which is the least, and then we have the next one, W1, and then, okay, so maybe we're done. Maybe W just equals the set containing W0, W1. But if not, then W minus those two elements is not empty. So what do we know about those elements? Well, they all got to live up here, right? They're all bigger than these. But is there a next one, or can I do the rational thing? There's a least one, right? There's a least next biggest one, because this has a least element. Right, and this process can continue. Right, you can keep going, like until you run out of W would be the idea. Do we necessarily, like, stop? Does this process halt at some stage? Like, do I go, I'm done now? Or maybe, maybe not. So which of the, what would tell you whether or not you're going to run out of diagram here? If W is finite, right? Like if W is finite, this diagram will stop. If W is infinite, it'll keep going. Okay, so it'll keep going, and it will start looking like the natural numbers, right? We've got 0, we've got 1, we've got 2, we've got 3. Let's say we've got a whole copy, it goes up forever. Are we necessarily done? So this keeps going. Right, so I cut out the least, I cut out the next, the thing bigger than the least, I cut out the thing two bigger than the least. I do that forever. Could this be non-empty, or must it be empty? Tell me, what do you think? So we've got an empty. We've got one vote for empty. It's hard to tell, right, from the definition. If this was non-empty, what does the diagram have to look like? Yeah, it means that, like, this keeps going, right, and then it kind of, there's like a limit process. So suppose I switch this in here. And then, okay, so if this is non-empty, what do we know about it as a set? Like, it has an element, right? And in particular, I would know it would have a least, right? Because it's a non-empty subset of a well order and so on. Okay, so as a test-taking skill thing, if everything that was called a well order was either finite or looked like omega, I wouldn't give a name to it. Right, so there are more by test-taking skills. Right, like I would. Yes, indeed. Right. So the idea is here is you can actually continue. If I add this, that's on top of everything. This is still a well order. So the thing would be W infinity would have to be bigger than everything here. And then here you have something that looks like a copy of the natural number. So that's still a well order, it turns out. It's not obvious that it is. You have to check the definition. And then you can ask the question, well, I've got this omega infinity. Am I done? Or could I keep going? Right, maybe you're done, maybe you're not, right? But if you're not done, then I've got an omega infinity plus 1, which lives on top of it. So well orders, they look like they've got copies of the natural numbers that are kind of stacked on top of each other. And then maybe they end with a little finite piece. That's sort of the idea of them. Because you can always keep listing them one by one in increasing order. Okay, so this process of listing them out one by one, if W, we don't have a formal mechanism for making sense of enumerating beyond infinity yet, right? We can list out by 0 and then 1 and then 2 and then 3 and then 4 because we have omega, right? That indexes that process for us. But we can make sense of listing things out beyond infinity, right? There's an intuitive sense in which it makes sense. All right, so well orders are the things which index this kind of process. So you've got some iterative process where you have stages, and you do things at each stage, and then potentially you're not done after infinitely many stages. Mostly in your mathematical lives, if you have an infinite process, then your object, your limit object, that's what you wanted. Right? Like, if you have a sequence of reals, right, and you want its limit, you only have to look as far as omega. But when you end up in more complicated situations, if your sets are bigger, then you've got to keep listing. Okay, so well orders are the kind of things that will index these processes, which are potentially longer than omega in length. Okay, so this is what they look like. You could keep going. They get quite complicated as objects. In fact, it's hard to think about it, but there are uncountable well orders. Provided choice. But actually, no, not even needing choice. Okay, so this is our intuition. We're listing them out one time after the other. There's always a next biggest thing. There is not always a previous thing, right? This has no previous thing because it's the least. But if this guy exists, then it has no previous guy, right? Because W7 is smaller than it, but W8 comes between. Right? And W8 is smaller than it, but W9 comes between. So in a well order, you can talk about successor, but you can't necessarily talk about predecessor, which is an irritating feature about well orders. Okay, so here's some notation that'll help us talk about well orders a little better. This is pure notation, no theory here. Okay, so I'm tired of writing angle brackets, everyone. I'm done. We're going to parentheses. All right, so this pair, you can encode it as a set theoretical pair if you want. The idea is I'm just telling you, here's a set, here's a relation. I'm handing you both at once. This is how am I defining this? Well-ordered set or I hate this, woe set. What's common is po-set for partially ordered set, and then the book says, people also say low set for linearly ordered and woe set for well-ordered. And I don't know, the book can say that. I've never heard anybody use this in the world, but I'm probably going to use it now because I'm a tired and old man. So this is a woe set if less than is a well order on W. Okay? So now I'm going to hand you the set and the order together. Right? That's pure notation. Okay, and then an initial segment, I-N-I-T. Oh, I need to scroll down, don't I? Whoop, 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 whoop. Okay. So an initial segment of a woe set. Now we've seen initial segments before. Do you remember? We have. You're all shaking your heads at me. I think Dedekind cuts are initial segments. Maybe I call them closed downward. So an initial segment is a closed downward set. So, having a good time there even? So an initial segment of a word set, W is a set V which is closed downwards. Now I've definitely mentioned closed downwards before. Closed downwards being, if you are in this subset and there's something less than you, then that's in the set too. So it has no holes downwards, right? It's not Swiss cheese, it's like cheddar. There you go. connecting with the students through the lens of cheese. So initial segment of a woe set is the set which is close downwards. So in this picture here, that is an initial segment, right? But if I take W0, W1, W2, and W infinity, that's not an initial segment, because there's holes between things, okay? Okay, and then isomorphism. We don't want to do algebra in this class, but here we are. So woe sets. There's also the unfortunate feature that W's and omegas can sometimes look alike, so I apologize if they do. If you're confused, just ask me and I will, but that's not supposed to be an omega, that's supposed to be a W, for instance. So woe sets are isomorphic. Now, I've used that word before informally. If you haven't seen it before in your mathematical lives, iso means same, I think, and morph means like shape. So you can compare with other kinds of, if you take an algebra class, you'll look at many kinds of morphism, like isomorphism, homomorphism, epimorphism, monomorphism, endomorphism, and they're all functions which preserve the structure that is being considered, and maybe the functions have a bonus property. And iso tells you that the function is a bijection. So for us, an isomorphism, in particular, it's an isomorphism of orders. But so woe sets are isomorphic if there is a bijection. My little chalk is receding into its little folder. F from V to W. Oh, I've written it the other way around in my notes. That's unfortunate. From W to V. It's the same, right? By the inverse. There's a bijection W to V such that W is less than W prime in the W relation if and only if their values are less than one another under the V relation. Right, so like over here on the left of this if and only if, you're trying to check a comparison in W. Right, and then over here, we're checking the comparison of other things in V. Right, so the idea is, as far as the order is concerned, these two sets are basically the same. So an example of isomorphic sets would be take W012 and less than is the element relation, for instance. Right, so this is the standard less than relation on this set, right? So 0 is less than 1, 1 is less than 2, nothing else, welcoming transitivity. And then something isomorphic to it, well, it's a bijection, so it has to have 3 elements. 72, I don't know, 10, 100, 1,000. Also under the element relation, which is the standard less than relation restricted to this set. So these two sets are actually isomorphic as orders. Via the isomorphism, 0 goes to 10, 1 goes to 100, 2 goes to 1,000. Because then things are less than each other here if and only if they're less than each other down here, right? So the idea is, for isomorphic structures, if you drew this diagram, it's the same diagram. They're just labeled differently. Right? So the diagram for this guy is 0, 1, 2. And the diagram for the second guy is 10, 100, 1,000. Right, but they're the same diagram, right? 3 dots in a row. So they're isomorphic. And the only thing that's changing is what you are using to represent the dot. But that's not really important as far as the order is concerned, right? The order only doesn't care about like what you label the objects that are being ordered. It just cares about which things are related to other things. Okay, so there are some things we can prove about isomorphic linearly ordered sets. For instance, if a set is finite and linearly ordered, then you have another set which is finite and of the same size and linearly ordered, they're necessarily isomorphic. So for linear orders, right, there's only one way to linearly order 3 elements up to isomorphism, right? I could like rearrange the elements, but they all look like this, right? And that just, up to renaming, they look like this. There's no other way to linearly order 3 objects. I could partially order them like this, right? Partial order there. Not linear though, because these two aren't comparable. Okay, so finite linear orders, there's only one of each size. But countable or bigger linear orders, there's more than one of each size. For instance, omega is linearly ordered, in fact it's well ordered and countable. But this omega plus an infinity is also countable, right? I've just added one new element to a countable set. And it's linearly ordered, it's well ordered, but they're not isomorphic. Intuitively, because the diagrams don't look the same, right? Like omega doesn't have an element on the top. But what that actually means is that there's no function from this set with the infinity to omega which preserves the less than relation. Right? We know there's a bijection because they're both countable, but it must necessarily mess up less than somewhere. Right? And it necessarily messes it up here. There's nothing that looks like infinity in omega. Okay, so if infinite things are not isomorphic, it's not necessarily because they're of different sizes. It could be because their orders are fundamentally different. Similarly, I guess, the rationals are not, I mean, this is, I said Woe sets are isomorphic. This is actually an isomorphism of just linear orders or even of partial orders. I only care about well orders. But the rationals is not isomorphic to either, the reals, because they're different sizes, there's no bijection at all. But it's not isomorphic to the integers too. Just because the diagram for the integers looks different, right? There are gaps in the integers that you can take a step. You can't take a step in the rationals, even though they're both countable. Okay, so what do I want to claim? Oh, I have a fact. This is the kind of fact that I don't want to have to prove, so I'm not going to. So I'm making it homework. Fact. So every proper? Yes. Every proper, every proper initial segment V of W. Okay, so by proper I mean, so initial segment means you're closed downward, right? Proper means you're not equal to all of W. So proper. So you're missing something that's necessarily near the top because of closed downwards. Is of the form it's the collection of things less than something. Okay, so W is the set of these in our big order, which is strictly less than some W. And we write this, we denote this set somewhat irritatingly with the square brackets. I'm sorry. We've run out of brackets now. I have to start reusing them. I don't mean function application here. So, okay, what do I mean by this? Pick an element of W, think of all of the things strictly less than it. That's necessarily an initial segment. What I'm saying is, if you have a well order, all of the initial segments look like that. This is not true in non-well orders. You can think about it. But if the idea is, let's say you've got a proper initial segment of a well order. That means there's something not in that initial segment, right? Because it's proper. And that means there is a least such thing, because I'm a well order. Right? And then my initial segment will be the set of things smaller than the least thing not in the initial segment. So there's your homework exercise. What we do, understand and prove that. Scribbling down, like, oh, this is pertinent for homework. There's points on the line. All right, so, question?
Yeah, sorry, I just want to make sure. So we're conversely, like, given an element W.
Yeah. This works even for a linear order. Both of them, yeah. They're being the equality is well orders only. In fact, that's actually an equivalent way of saying you're a well order. Is saying, but that's a bit of a pain to prove. Okay, so I have all this terminology, and the idea of bringing up all this terminology but keeping it vague is that I can hopefully you will intuitively believe the next theorem, which I have no intention of proving in detail. See, it says proof sketch to indicate that we're not going to do it properly. And then we're going to take a break after I state it anyway. In fact, let's take a break now. Let's go wild. Take a break right now. All right, folks, no more break for you. End of break. Okay. So back to the theorem. I'm not going to prove in detail. I'm just going to give you the intuition. And I might not even make you do it on the homework like I did for all of the other hard theorems. Okay, so trichotomy theorem for row sets is, hopefully trichotomy theorem tells you what to expect. So if I have two different row sets and exactly one of the following holds. Okay, number one, V and W are isomorphic. So they're the same as far as the order is concerned. You've just kind of relabeled the objects that you're ordering. If that doesn't happen, then two possibilities. W is isomorphic to an initial segment of, sorry, V is isomorphic to an initial segment of W, or the other way around. That's it. Scroll down. Oh. It's not really much use showing you the blank handout, right? If it's making up for the absence of the homework in front of you. Ah well. I'm committed to using this at this point. Okay, so trichotomy for row sets basically says there isn't really much in the way of difference about them. If you have two of them, either they're the same or like one is shorter than the other, is how we interpret these two. In a very formal sense, right? Like the shorter one is just a relabeling of an initial segment of the longer one. Okay, so my proof sketch here is basically the picture that I erased, but you do it on both the sets at once. So you start listing out the elements of W and the elements of V in increasing order. And we're going to match them up. So the least element of V has to go with the least element of W. Right? Otherwise, I'm not going to get an isomorphism, right? Because to preserve the less than relation over here, the least thing before has to be the least thing after. Okay, so sort of V0 has to go with VW. And we ask, am I done enumerating one of my sets? If not, then there's a V1 and there's a W1, right, which are the next biggest thing. And then I have to match those up together to preserve the order relation. You ask, am I done enumerating my sets? If not, there's a V2 and there's a W2, right? And you keep doing it in that fashion. So the intuition is eventually one of the sets runs out of elements. Maybe they both run out at the same time, in which case they're isomorphic. Or maybe W runs out first, in which case W is isomorphic to an initial segment of V. Or maybe V runs out first, in which case it is isomorphic to an initial segment of W. That's it. So right, so your isomorphism has to do this, right? It has to preserve order everywhere. And the idea is both of them have this diagram that always looks like this, and one of them runs out first, or they run out at the same time, right? And that's going to give you the trichotomy. Okay, and that is the sketch of the proof. Okay, that's the idea. So we're going to build this one by one. Now, you might be... So what I'm doing here is I'm sort of like I'm picking pairs one by one and adding them to a set, right? And sort of building an isomorphism by adding elements one at a time. And that sounds a bit like the recursion theorem and a bit like, to me, right? Like I'm building something one by one. But the problem is W and V might be longer than the natural numbers, right? I might not be done after omega many steps. So how do you formalize this process? And it's super slick, actually. What we do is we let F be the set of pairs, which are round of everything. So I just pick the set of input-output pairs such that the corresponding initial segments are isomorphic. That's ISO for isomorphism. Sorry, I'm being lazy. And this describes, in one very short step, how to line these up. Right, so the isomorphism, the initial segment below the least element is the empty set, right? There's nothing strictly less than the least element. So those two would be paired up. And then there's the one, right? The thing that's not least, but it's one more than the least. Its initial segment has one element. And so I line those up. Right? It's very slick, right? So one can show this is a function, and it preserves the order, and its domain and range are subsets of W and V respectively. In fact, they're initial segments. And then you can show, the final thing to show is it isn't a proper initial segment of both, which is the pain in the butt, right? So either the domain of F is all of W, or its range is all of V, or potentially both, right? And if the domain of F is not all of W, then technically you have to turn it around, right? Because then it's an isomorphism from V to an initial segment of F. Okay, so this is the very slick set theory way of doing this intuitive idea all at once. But we're not going to prove this has any of the properties that I just said it has. So I don't want to. Okay, so the intuition here is that well orders are themselves sort of comparable under length. And you might think like, okay, can I make a set of well orders and then compare them under this way, right? Like say like a well order is smaller than another well order if I can embed you as an initial segment. And you very nearly can, except that set's too big, that's all. It's just too big to be a set. Otherwise it's completely fine. Like this, it looks like we can linearly order well orders. And we can, except that the set is too big, that's all. It has all the properties of of like a linear order, though. Like every well order is comparable in exactly one way. This order is transitive, it turns out, right? Like if V is an initial segment of W, is an initial segment of U, then V is an initial segment of U, which is transitivity, so on. The crazy thing, though, is that well orders, not only are they sort of linearly ordered, they're actually well ordered. Ooh, spooky. Okay, so if you have a collection of well orders, there is necessarily a smallest under this notion of smaller, right? Okay, so we could just keep talking about well orders, but it's convenient to pick a particular well order of each length and say this is the guy we're going to talk about now. Much as with the cardinality stuff, right? We could just talk about cardinality by saying, you know, this is abbreviations for there are bijections between, but it's convenient to say, no, cardinality means this particular one. Okay, so we're going to do the same with well orders. And the ones we pick are called the ordinals. Whee! That's a very illuminating bit of slide there. Okay, scroll down. Okay, so what does it mean for a set to be transitive? Not a relation, a set. Every element is a subset, right? Yeah, that's one way of saying it. Elements are subsets, or if you're an element, then you're in the union, or if you're in an element, then you're in the original. Right, they're all equivalent. Okay, so X is transitive if little x in X implies little x is a subset of X. Not the other way round. That's not possible. People who made this mistake on their second midterm, which was a lot of you. I don't know if it was any of you in particular. It was anonymous grading, but probably thought this went the other way. It can't. Homework 1. This cannot be turned around the other way, right? Because then you'd be equal to your power set. Okay, so you're transitive, if that's true, and now we can define an ordinal. So a set alpha, we tend to denote ordinals by lowercase Greek letters from the early alphabet. So like alpha, beta, gamma, delta, epsilon if you're having a really bad time and you need 5 different ones. So a set alpha is an ordinal if 1, alpha is transitive, and 2, the important one, you just looked scared, so I decided to blame you. Whoever it was, you're very bad. Transitive, and 2, alpha is well ordered by the element relation. Okay. So, we've actually already built a bunch of different ordinals. We've even observed that they have this property. So, examples. Omega is a transitive set that is well ordered by less than. In fact, that was the definition of omega, right? It's the least set with this property, right? It's the intersection of all inductive sets, so necessarily it's the least infinite set with this property. Okay, so omega. Also, all natural numbers are transitive. We proved that by induction. And they're well ordered by the less than relation. Okay, so those are ordinals. An example of a thing that's not an ordinal would be like 1, 2, 3. I did that mistake, I always do. Just to write a set bracket instead of a 3. This is not an ordinal, because it's not transitive. It doesn't contain 0. That's the thing. That's the problem. So, and like 0, 1, 2, 3, 6 is not an ordinal because it's not transitive, right? Because if you contain 6, you should contain 5 and 4 and 3, and 2 and 1 and 0. Yeah. Okay, so those all work. Good. I'm going to rearrange this lemma and proposition because the lemma's the good one. Yeah, it's a lemma. This I'm going to make homework because it's important, but I don't want to do it. If alpha is an ordinal, then its successor, we're coming back to successor, it's not gone away, is an ordinal. So the idea is, you've taken alpha, which is well ordered by less than, and you've sort of added something bigger than everything else. So you kind of like, you've extended your well order by one step. That's the idea. So if alpha is already transitive, this is transitive, and if alpha is well ordered by less than, this is well ordered by less than as well. Yes?
When you were talking about like the next group of infinite many things, is this like putting the natural number is omega in omega?
Yes. So like, so this thing is the thing that I drew with the omega infinity. And then if I wanted to extend it again, right? So you keep tacking on an extra element bigger than everything previously. So if you have a well order, I think it's intuitive that if you stick something on the end, right, bigger than everything, you still have a well order, right? Because you haven't messed up every non-empty subset being having a least element, because it's bigger than everything. So the only thing to worry about is transitivity. But that's not really hard to prove. I mean, like, so checking your well order is still a bit tedious. It's just like not hard. There's just lots of things to check. Yeah, so this can keep going forever. And then if you wanted, you could be like, sort of, can I take a limit here? So I have like a copy of omega, and then sort of the limit happens, and I have another copy of omega. And you might think of that as like omega plus omega. And eventually we will think of it like that, literally. Okay, so roughly speaking, all ordinals are built sort of in this way. You start with the finite, with the empty set, you take successor sort of forever, and then you like take the limit, which means union here. And then you start building successors again forever, and then you take the limit. And they all do that forever. The problem is, like, taking the limit might be a limit over an uncountable set. So it gets more complicated than you think. The intuition's good though. Okay, so that's our little lemma. This is our homework. Hooray, for me. But now an actual proposition. You're all going to like this proposition a lot. If alpha is an ordinal, alpha is not in itself. You know why you're going to like this? Because you all want to assume this about every set anyway. And I keep saying, no, you're not allowed. Okay, but if you're an ordinal, then this is true. And the proof is very, very stupid. You assume that it is, and we derive a contradiction. All right, so the idea would be, if not, then alpha is in itself, and that means the set containing alpha is a subset of alpha, right? If you're in yourself, then the set containing you is a subset of yourself. What's the least element of this set? Right, it must have one. It's a non-empty subset of alpha. It's only got one element, so it must be itself, right? But it's less than itself. because it's in itself. Right? Because basically, we have defined well orders to be strict less than. But this is suddenly a non-strict thing, right? It's something that's in itself. So it has no least element. No strict least element. That's one way of thinking about it. I guess another way that might even be simpler is this breaks like the fact that strict linear orders are necessarily irreflexive, right? No element in a strict well order is less than itself. Is it strict? But then this is in itself? Contradiction. Maybe that's even more direct. So better. Yeah, in fact, then it's immediate, right? Like if in is supposed to be strict less than, then nothing can be in itself because it has to be strict. Anyway, I'm overcomplicating a theorem. That's unfortunate. So I try my best to not do that. So. Okay, so if we have an ordinal, then we can make this one that's bigger. We call this the successor of it, because it is the next biggest one. It turns out there's nothing in between. And we'll often write, instead of alpha plus, we'll write alpha plus 1, as if we're adding 1 to the end. So we will denote this alpha plus 1. And if you want alpha plus plus, we can write that alpha plus 2. And all of this will make sense. In fact, we can even formally define how to add ordinals in this way, and it all works out. So you can use the notation that you would expect. So if I hand you an ordinal, you can ask a question, are you the successor of something? If so, you're called a successor ordinal. If not, then we call you a limit ordinal. So an example of a limit ordinal is omega. Right? Omega is not 1 plus anything. Also 0 for a stupid reason, because it's not 1 plus anything. So limit ordinals are not successors. Successors are successors. All right. So here's the theorem that, again, I don't want to prove because we don't have time. And I don't think it is very fun. So, but we can write out what the conclusions of the theorem are. Okay, so number 1. If alpha is in beta is in gamma, what do we know? Oh, sorry. I've written less than. I better define that. For ordinals, less than means in. Okay, so as with natural numbers and with omega, I'm going to use less than to be in, right? So, because I'm using the less than symbol, we would hope that it satisfies certain properties that the less than symbol satisfies. Okay, so if alpha is less than beta is less than gamma, then alpha is in beta is in gamma, therefore what? Alpha is in gamma, because what would imply that? So this is what we want. Right, this is what we want, right? Because I'm writing using a symbol which is transitive, I would like the relation to be transitive. So what would tell me that every element of every element is in the original thing? The first axiom of being an ordinal, right? They're transitive. All right, so because they're transitive as sets, they're transitive as relations. And we finally see why we use both words for both. This is why. Because being transitive as a set means on ordinals, but comparing them is a transitive relation. That's sort of why at the end of the day. Okay, so 2, if alpha is less than beta, well, it might not be obvious what we want to conclude here, then beta is not less than alpha. Because if they were, then alpha is less than beta is less than alpha, so alpha is in alpha, but we already contradicted that, right? That's not possible by transitivity and irreflexivity. Exactly one of Fill in the blanks. So alpha is less than beta. What are the other options? Sorry, alpha equals beta. I've given it away. No, by my inability to speak. So if I have two ordinals, then necessarily one is in the other. That's not entirely obvious, but it's really helpful. Every non-empty set. This is not an obvious thing again, but it is true. Every non-empty set of ordinals has a least element. So these four things here, they say that ordinals are linearly ordered. That's the first three, right? And in fact, they're well ordered. So you might think the ordinals are a well-ordered set. And that's very nearly true, but what's going to be the problem? If there's going to be a problem, and it's a set theory problem. So what's the only thing that kind of stops things that look like equivalence relations from being equivalence relations, Tony? Or similarly here?
Oh, sorry. I was gonna say, I thought you were gonna say something like, there's a Russell set.
There is, yeah. It's too big. It's too big. Yeah. So the set of our ordinals is too big, unfortunately. That's called the Bernoulli-Fortieri paradox or something. It was the first paradox of set theory that came out. Was somebody said, well, a set of our ordinals can't be a set. Then it ends up sort of being in itself. Okay, so apart from the fact that, so technically all ordinals is a class, it looks well ordered alike. But the fifth property is that if X is a set of ordinals, there is an ordinal alpha not in X. So that's another way of saying there is no set of ordinals, right? If you collect together a bunch of ordinals in a set, you've necessarily missed at least one. Okay, so these are some facts about ordinals. We don't have time to prove them, and so we're not going to. I'll see if I want to cover them on Thursday. Otherwise, it's end of class. 10:14. Look how on time we're ending. All right, so that's, get out of here. Yeah.